Hi, this is Dane Quinn from the University of Akron, and today's video lecture will focus on a technique for estimating system parameters known as logarithmic decrement. One of the central tasks of engineering mechanics is prediction, right? It's being able to compare analytical results that we obtain from some model with experimental results. So how do we do that? Well, we start off with the physics, right? We look at the laws of mechanics and we make some assumptions. We identify parameters. We go then and determine an appropriate model, solve that model, and finally compare those results with, again, experimental results, right? So essentially we start over here on the left and we work our way to the right. Again, this is basically prediction. However, we could do this kind of in reverse. And the idea is to ask the question, what's the best model that fits experimental results? What are the best physical parameters to use? Essentially, all those things that we usually start off with, we could ask, can we obtain those? Can we obtain estimates for those from the actual experimental results that maybe we have? Right? So we might start off with experimental results and again work our way back in this process and ultimately estimate the model that best fits those experimental results. So again, here now we're talking about identification. These kinds of problems are known as inverse problems, right? And they are the inverse of what we typically do, right? They look to identify the model from the measured response as opposed to starting with the model and developing the analytical prediction. Or, in some other cases, maybe even find the best approximation to a physical system. After all models are approximations. And modeling really involves making good assumptions about the important effects that go into a representation for the experimental system. Right, so again, this forward path is what we're typically familiar with, right, and that's prediction. And then the inverse path is identification. Today, I'd like to kind of look at this identification problem in the context of something that we're very familiar with, which is, of course, a spring mass damper system. So here we have a mass, M, spring stiffness K, B is the damping coefficient. I'll measure the response with X. And then we find that the equation of motion is given here, right? We've seen this a lot, right? Mx double dot plus bx dot plus kx equals 0. So then solving that, we can develop a response. And that's shown over here on the right. So this would be a typical underdamped response. Right? It oscillates as it decays. And of course, I can solve this, right? And I know how to do this. We've had lectures on this. And the solution looks like some amplitude, right? We have an exponential decay term, e to the minus sigma t. And then we've got an oscillatory component, damped natural frequency omega d. Notice that there are really two parts to this, right? One part involves the system parameters, right? Here, this would be represented as sigma and omega d. There are other forms that we'll look at. And then the second aspect of this is initial conditions, right? So x depends on the initial conditions, and theta, the phase shift, depends on the initial conditions for the problem. But if I'm looking for a model, really what I'm focused on are these system parameters. So the real question that we ask is, given the system response, right? So that would be x of t. Maybe this is a measurement that we take from the lab, right? As opposed to, some predetermined function. But again, if we have only this measured response, can the system parameters be identified? So again, the physical parameters are M, the mass, B, the damping, and K, the stiffness. So can we identify those from our measured time trace. And this method, logarithmic decrement, is one way of helping us do that. So again, we'll start off with the equation of motion. In this context, right, I assume that this is the exact model, right? And although I don't know the parameters, right, I do know the results of that model. So, one thing we do to simplify this is that we factor out the mass. And then what's left is our equation of motion in kind of standard form, right? So it's x double dot plus, well, then this term would be b over m, but we choose to write that as 2 zeta omega n. So we're going to use the damping ratio and natural frequency here. And then omega n squared times x is equal to 0. Of course, omega n squared is just k over m. This will be kind of our standard form that we'll use. And the reason that we really focus on this is because the response is determined entirely by zeta and omega n. So those are, again, the damping ratio and natural frequency. So it's these, and of course, the initial conditions. For an 100 amp system, again, if zeta is less than 1, then I can actually write the solution, right, as I've done over here. Right? So x of t is, well, it's an amplitude which depends on initial conditions. E to the minus, let's do those system parameters in green, minus sigma times t. Sigma is the decay rate, and then sine of omega d, which again is the damped natural frequency, and finally the phase shift, which again depends on initial conditions. Using sigma and omega d as system parameters, we have this. Well, we can also relate these back to zeta and omega n, right? Remember that sigma is zeta times omega n, and omega d, the damped natural frequency, is the natural frequency times 1 minus zeta squared. Again, this response depends on system parameters and initial conditions. And, down here in this figure, I've kind of tried to highlight one of the issues. That is, the response is very different depending on the initial conditions, which I really don't have any control over if I'm just taking a trace from the lab, say. Given different initial conditions, we might get this dark blue line, or this lighter blue line, or the gold line, or any number of different kinds of responses. So we'd like to come up with a way that essentially filters out the amplitude and phase shift of the response and allows us to determine uniquely the damping ratio and the natural frequency. Because I really don't want to mix these two things together. So that's ultimately the goal here, right? Identify the damping ratio and natural frequency from the measured response. So again, that's x of t. And we want to do this in such a way that it's independent of initial conditions. Of course, the initial conditions influence the response, right? But I want to develop a technique that doesn't rely on me also solving for these additional two unknowns. Right? I only want to be able to focus on the things that I'm interested in. So that's the method of the logarithmic decrement. Now, how does this work? Well, it basically starts off with the general solution, right? So here, x of t is given as we've seen before, and I can always take a derivative of that and find the velocity, right? So when I do that, right, I get this expression here. Now, notice that I'm combining a sine and a cosine function, right? So when I do that, I can actually pull those together into one harmonic function. And that's what I've done down here. So when you go through the math, right, you end up finding that this term in brackets is omega n times cosine of omega dt plus theta. And then there's an additional phase shift, eta, right, that's given here. So there's some algebra involved in this. But what I really want you to focus on is that the harmonic piece here, the harmonic function, is just a cosine with an argument that has frequency omega d. Why is that? Well, because what I'm interested in are easily measured places, right? I just want to take a couple of measurements here, right? So what would be a good measurement to take? Well, it's easy to identify the maximums, right? So that's the first time we get a local maxima, right? And we'll identify the time as t1, right? So that's, say, t1, and then the value at that time is going to be x1. And I can also identify the next maximum, right? And we'll call that t2 and x2, and I can keep doing this, right? So we'd have a t3 down here and an x3. And again, the reason that I'm doing this is that they make convenient points, right? It's pretty easy to figure out where the maximum are and then measure the time and measure the amplitude, right? So given these points, I'd like to be able to say something about the response at these values. And again, what do we know about maxima? Well, at maximum points, the velocity has to vanish. Right? I mean, that's the definition of a maximum. So looking at this expression for the velocity, what we find is that that implies that cosine omega d times t sub I, right? So I'll just look at kind of any of these maxima as t sub I plus theta plus eta has to be equal to 0. As a result, we can actually solve for these times in terms of the damped natural frequency and then these other two phases. Right, so here, omega d times ti plus theta plus eta has to be pi over 2, or some multiple of 2 pi thereof. Right, so this would be, I is equal to 0, or in fact plus or minus 1, or plus or minus 2, or so forth. The negative sign would be like going backward in time. So again, this is the relationship for all of these various times. We also know that this vanishes when the argument here is minus pi over 2, and that would correspond to the minimum. Here I'm only focused on the maximum, which is why I'm only taking this value as pi over 2, plus, again, 2 pi. Let's look at successive maxima. So, again, maybe T1 and T2. Here, T1 corresponds to I is equal to 1, right? So we'll just put I equal to 1 right in here and solve for T1. All right. T1 is then 1 divided by omega d times pi over 2 plus 2 pi, right? Again, we're just going to use I equals 1 minus eta minus theta. The next maximum would be for I is equal to 2, right? So that's T2, 1 over omega d. Going through, the only difference here is that now, instead of 2 pi, I have 4 pi. And then, again, minus eta minus theta. Looking at the difference between these two, T2 minus T1, well, all of these phases cancel out, right? So I've got here an eta here, I've got another one there. The pi over 2 drops out. And in fact, 4 pi minus 2 pi is equal to 2 pi divided by omega d. And this is defined as the period. It's the period of the oscillations. Hey, this is really nice, actually, because this period is easily measured. I can just, again, find the time between successive maxima. And looking at that, it only depends on the system parameters through omega d, right? It's independent of the amplitude or, in fact, the phase shift. Even though the phase is part of T1 or T2, when I take the difference, right, that phase drops out. So this is nice, right? It's a relationship that relates something easily measured to the system parameters. Now, we can develop a similar thing by looking at the amplitudes. Right? So here, if I take T1 and determine the corresponding displacement, right, we would find that x1, right, which again is x of T1, is amplitude times e to the minus sigma T1 sine omega d T1 plus theta. And so when I take this expression for T1 and substitute it in, right, this sine piece simplifies considerably. E to the minus sigma T1. I end up with actually just cosine eta, right? And you can go and pause this and do a little bit of algebra and convince yourself that this expression, when evaluated at T1, reduces to cosine eta. If I do the same for x2, right, again, that's x at time 2 minus sigma T2 sine omega d times T2 plus theta, and this simplifies e to the minus sigma T2 times cosine of eta. So why is this useful? Well, we would like to, in some sense, eliminate this unknown amplitude. And we can do that really by just dividing these two by each other. So x1 divided by x2, well, let's rewrite that. And let's rewrite the bottom. And look what happens, right? This term cancels out, as does the cosine of eta. So what we're left with, actually, is e to the minus sigma times T1 minus T2. And that, in fact, is just e to the sigma t, right? Because, again, T2 minus T1 is equal to the period. Here I've written those two relationships again. So this is the period, right? It's 2 pi over omega d. And then x1 over x2, that's the ratio of successive peaks. And that equals e to the sigma t. This is nice. I've got things that are measurable and system parameters. And in particular, I don't have any dependence of these two relationships on the initial conditions. Here we would like to reduce this. So what we'll do actually is just take the natural log of both sides. Right? So the natural log of x1 over x2 is equal to the natural log of e to the sigma t, and that just equals sigma t. So this quantity on the left, this natural log of x1 over x2, we actually define as delta. And delta is known as the logarithmic decrement. So again, t and delta can be measured from the response. T is just the time between successive peaks, and delta is the natural log of the ratio of successive peaks. As a result, we can solve these two expressions for the system parameters. Well, looking at the period, we see immediately that omega d is 2 pi divided by the period. And so that's going to be, again, omega n square root 1 minus zeta squared. Sigma is delta divided by t. And that, of course, sigma is zeta omega n. So I can now go and reduce this further and identify the natural frequency and the damping ratio. Right, so let's look at our expression for the logarithmic decrement first. Right here, delta is equal to zeta omega n, right, times t. Okay, well, from here, we find that the period t can be written in terms of zeta and omega n using this relationship, right? So it's actually 2 pi divided by omega n square root 1 minus zeta squared, right? Because that's equal to t. This is nice because the natural frequency drops out. And as a result, we're able to write this as 2 pi zeta divided by square root 1 minus zeta squared. So now I see that the logarithmic decrement is in fact only a function of the damping ratio. Now I'd like to basically invert this relationship and solve for zeta. So pause the video now, maybe work through that algebra, right? And what you'll find is that in terms of the logarithmic decrement, delta, the damping ratio is solved as delta divided by square root of 2 pi quantity squared plus delta squared. And likewise, I can then go and solve for the natural frequency as 2 pi squared plus delta squared divided by t. So given the logarithmic decrement and the period, which again are measured from the response, I can determine both the damping ratio and natural frequency with these two relationships. So in particular, if I go and I plot the damping ratio as a function of delta, right, I end up with something that kind of starts off at 0 and approaches 1 as delta increases. Right, so again, if delta is equal to 0, zeta is equal to 0. Well, that makes sense. If there's no damping, then the ratio of successive peaks is 1. Well, natural log of 1 is equal to 0. Right, so again, no damping, I see that delta is equal, or zeta is equal to 0. Delta is equal to 0 as well. And then the natural frequency would just be 2 pi divided by t. Okay, well, because that's the period of the oscillations. As delta increases, right, we find that the damping ratio approaches 1, right? So as this ratio gets larger and larger, right, which means that basically the second peak gets smaller and smaller, then the damping ratio approaches 1, while the natural frequency, again, given that period, would end up getting very large. In its most basic form, this is the logarithmic decrement, right? So we have relationships for the damping ratio and the natural frequency that we can identify from the measured response. When we developed this in the previous slides, we took the first and the second peak. We can generalize this really to any pair of peaks, right? So let ti be, the first peak, so that I could be 1, right? Or I could be 2, and then look at the k peak after that, right? So here, if we were to take 2 and 3, right, then I would be 2, and then k would be 1. So we were taking t2 and t3. Or we could take peak at t1, and then we could skip a peak and take the second peak, right? So that would be like saying t3 minus t1. When we do that, and we go through all the math again, right, we find that the time between peak ti and ti plus k, right, so k peaks after this, is just 2 pi over omega d, which is, again, the period of the oscillations, times the number of peaks. That kind of makes sense, right? I was going once, now I'm going twice. And then the ratio of those peaks is equal to e to the sigma, and then again, the time between peaks again. And we can do this for any pair. We can do it again for successive pairs. Well, it works out clearly if we choose 1 and 2. We could do it for 2 and 3. We could do it for 1 and 3. We could do it for 2 and 17 if we really wanted to. And when we go through, right, we end up identifying again the logarithmic decrement as the natural log of this relationship. Right? And of course, we'll put a subscript k, right? So it's defined as the natural log of xi and I plus k, right? So k peaks after that. And that's going to be sigma times the time between those two peaks. Once again, I can measure tk, right? So I could basically figure out the time between t1 and t3, and I can measure the logarithmic decrement, take that ratio and the natural log, and we can determine, again, the damping ratio and natural frequency. So if we do that, we would solve for the damping ratio as now delta k, and again, we're taking sort of these two new pairs. Denominator is 2 pi times k, right? So this is essentially the phase of all of those cycles, plus delta k squared. And likewise, the natural frequency is equal to 2 pi k quantity squared plus delta k squared, right? This whole thing divided by tk. So once again, right, we're able to estimate the damping ratio and natural frequency. And you could ask, right, why would I worry about that, right? I can just take T1 and T2. Well, yeah, that's true, right? And if the response is exactly represented by our second order spring mass damper system, so if it's determined exactly from, our mx double dot plus bx dot plus k x equals 0, then every pair ti xi and ti plus k xi plus k gives identical results. Right, so we would get the same value of the damping ratio and natural frequency, regardless of which two pairs we picked. But if the system is not exactly represented by this, and we're just looking for a good approximation, then those identified values will change, right? So multiple pairs, are multiple steps here. Well, it can be used to estimate how well the system is represented or is modeled by our second order spring mass damper system. And really, we can use sort of multiple measurements and multiple pairs, right, to estimate the best approximation. So from this logarithmic decrement method, we're able to identify the damping ratio and natural frequency. There is still a question about those physical parameters, M and B and K. Well, it turns out that we can't identify all three of them with this procedure because, after all, the response only depends on two quantities, zeta and omega n. Right? So there's no way that I can estimate three things from these two quantities. However, if I can figure out one of them by some other means, right? So maybe we can measure the mass. Right? That's often fairly straightforward, right? We'll just measure the mass. And then we can determine the value of damping and stiffness, right? So then we would find that K is M times omega n squared, and B is M times 2 zeta omega n, right? Where again, zeta and omega n are determined from this logarithmic decrement. So again, that's one way of estimating parameters for a system based on given experimental data or even given analytical results, right? Maybe somebody gives you the response of a simulation. And this can be very useful, right, when we're really trying to develop models for complicated systems. We'll do some more system identification later, and a lot of that will rely on things like the forced response of a system, right? But this is a very nice way of estimating system parameters, again, from the transient or free vibration of a system. So that's it for today. Thanks so much, and I will talk to you again. As always, any feedback is welcome and encouraged. You can leave a comment. You can send me an email. Love to hear what you think. Thanks so much. Take care. Bye.